thank you for attending. I think I will go through with the presentation really fast, and because I know that you are tired. My name is Shahla Atapoor, and as you can see, the title of our paper is Simulation Extractability in Groth, zk-SNARK. It is a joint work with Karim Baghery, and it is published in CBT workshop at ESORICS in 2019. I will start by some introduction and background, and then I will continue by our motivation behind this research, and talk about a bit about construction of our scheme, and I will end by showing some plots for performance of the new scheme. I will not go through the more details about zk-SNARKs because Professor Wittmann very nicely explained about them and talked with more details. Just for review, I would say that zk-SNARKs stands for zero knowledge, non-interactive argument of knowledge. In the CRS model of zk-SNARKs, we have three algorithms. CRS generator generates the common reference string, which is shared by prover for proof generation and verifier for verification of proof. There are some requirements of zero knowledge zk-SNARKs. First one is completeness. It means that if two parties are honest, everything should be done correctly. Next one is zero knowledge. Zero knowledge means that this honest verifier should not be able to learn anything about the witness. Should not be learn anything about the witness from the proof. And knowledge soundness means that this honest prover should not be able to convince the honest verifier unless she knows the witness. Succinctness means the proof size is short, the constant number of elements. Here are some statements. For example, a prover wants to prove that she knows the secret key for this public key. Public key is equal to G to the power of secret key. And for example, in some applications like Zcash, privacy-preserving digital coins like Zcash, in one step we want to give a proof that the private values of new coins are equal to the public value of old coin. This is written here, and so on. As you may notice, Karim in previous talk talked about the some more stronger notion that, of knowledge soundness, which is simulation knowledge soundness. But he talked about the black box simulation knowledge soundness, which is useful for UC security. But in some applications like Zcash, we just need simulation knowledge soundness. We just need to guarantee the non-malleability of our proofs. So we just want to stand with this property, simulation knowledge soundness. It means that it says that this honest prover cannot convince the honest verifier unless she knows the witness, even if she has seen arbitrary number of simulated proofs. And in our scheme, or in the schemes that they want to prevent malleability attack of proofs, they are using this stronger notion of knowledge soundness. By now, there are several zk-SNARKs which are proposed during the last decade. For example, Groth in 2010, Lippmann 2012, and Pinocchio by Microsoft in 2013, and so on. But the most efficient and the fastest one is Groth 2016, which is cap-based, but the problem with the Groth zk-SNARK is that its proofs are malleable. Then a year later, Groth and Muller, they proposed another zk-SNARKs, which guarantees the non-malleability of proofs, but it is sub-based. And since it is sub-based, square arithmetic program based, so it means that it is less efficient than Groth. And here you can see that in CRS size, in proof size, proof time, proof generation time, verification size, and verification time, in all of them, Groth-Muller is less efficient than Groth, but the good thing is that its proofs are non-malleable. Then it brought the thought to our mind that can we construct something between them? Can we construct something more efficient than Groth-Muller, but with non-malleable proofs? Fortunately, we answered this question positively, and we construct a new scheme, which is a new variation of Groth, which is slightly less efficient than Groth, but much better than Groth-Muller, and the proofs are non-malleable. I talked a lot about the Groth 2016 and Groth zk-SNARK. It is better to get coincident with, a bit with his zk-SNARKs. Groth zk-SNARK is the fastest one, and it is for cap-based. And it is cap-based, and it achieves perfect completeness, perfect zero knowledge, and computational knowledge soundness. It is based on bilinear pairings. Its verification dominates by 3 pairings, and it is secure in general group model, but the problem is its proofs are malleable. Let's see what do I mean by malleability. Here is the proof of Groth. Groth proof, as I mentioned, has 3 group elements, 3 elements, 2 from first group element and 1 from second group element, and its verification is something like this. It says that if a verifier checks that if pairing of A and B is equal to pairing of C and some elements from CRS or not. A very simple man-in-the-middle attack here is that adversary picks samples randomness and then multiplies the first element A with R and then multiplies the second element of proof, B, with 1 over R, and then you can see here that verification will be passed because these two R and 1 over R cancel out each other, so you can see that very easily it is kind of malleable. Let's see how we kind of prevent this malleability attack in our scheme. Intuition behind our scheme is that we use or folklore technique, which is proposed by Bellare and Goldwasser in '89, and they used a NIST plus Solarno function and commitment to propose the kind of unforgeable signature. And here we are trying to we are doing kind of the same, because in their case they wanted to have the unforgeable signature, which means that if the signer has seen arbitrary number of signature, she should not be able to generate or to give a valid signature if she is dishonest. And in our case, we want to show that if this honest prover has seen arbitrary number of simulated proofs, still she should not be able to convince the verifier. And here you can see that using the original language, we define the new language L prime. And for this new language, we have some new statements and some new witnesses, and such that this relation holds. Here you can see the pseudo-random function. If somebody knows this S, I mean by knowing this S, it is written here, by knowing this S, we can easily, for example, a simulator can easily simulate, with this part can simulate this protocol. And if somebody does not know this S, this pseudo-random function acts as a truly random function, and it is very difficult to break it. In the original scheme, there are 4 algorithms: keygen, P, V, and SIM. This is a simulator. And in our language, in our scheme, in new scheme, we have keygen prime, P prime, V prime, and SIM prime. I will not go through all the details. Just I want to mention that here, at some point, yes. Here we have just 2 more verification, because prover needs to kind of sign her proof. And here we have one verification more than the original one, which is checking the signature. We will see later how we can check it. I think you observed that we have commitment, pseudo-random function here, and we are the same as how can zk be instantiated this pseudo-random function and commitment with SHA-256, which has the kind of 25,000 multiplication gates, and we instantiated our signature with a Bonnevoyant signature, and here you can see that actually our verification pairings is 4 pairings, but the original case is 3 pairings. Actually, we add 1 pairings to our verification because of this signature. And still we are better than Groth because Groth has 5 pairings in its verification. Okay, here are some explanation, some numbers that you can see, and you can here you can kind of compare this Groth model and a new scheme, because they are kind of simulation extractable, and you can see that in all the proofs, CRS size, proof time, and everything we are better, but just in the case of the verification, our proof size, our theory size is a bit longer, but it is still better, but surprisingly our verification time is still better than verification time. And we plot we did them for 1 million gates, and it is for 128-bit security. Here are some plots for our scheme. You can see here, this plot is for multiplication gates, it grows by the arithmetic circuits multiplication gates, and this is for time. This dash dot line, red dash dot line is Groth model, and this black dash line is our scheme, and this solid blue line is Groth. And you can see that in CRS size, we are very close to Groth scheme and very better than Groth model. And here the plot is the same for different arithmetic circuits with different multiplication gates and the time. And here again in CRS generation time, we are very close to Groth. And in proof generation time, still we are better. And again, we plotted for by growing the multiplication gates in arithmetic circuit, and the time we plotted, and you can see that again we are better. And in this case, in verification time, we plotted with the size of statements. I mean that the size of statement will grow, and up to some point, this growing the statement dominated, I mean the verification time dominated by the pairings. And since we have one pairing less than Groth model, so up to some point, still we are better than Groth model, but from somewhere here to end, we are kind of same as Groth model, because this statement, this verification time from some point will dominated by the number of exponentials. And it is worth to mention that Karim showed that our construction can achieve subversion zero knowledge, and it will be published in a conference, IMACC conference in Oxford. And thank you very much.